Electrical machinery 1. DC generator. Characteristics of DC generator. Open circuit characteristics, external characteristics, load characteristics, and internal characteristics. OCC of self-excited DC generator. Circuit shown in figure. Generator is connected to ammeter and voltmeter and field resistor that is changing resistance and field winding. Shown in figure. Voltage is obtained by voltmeter reading and IF field current is obtained by ammeter reading. Resistance is changed using field resistor. Field dividing connected appropriate to armature of generator. Circuit shown in figure. OCC of self-excited DC generator. Graph shown in figure, that is IF versus induced EMF E in volts, or SH is shunt field resistance. Below line is or SH line. OCC curve shown in figure. Tangent of this curve is given value of critical field resistance value. Third line, that is load winding of rise. Field current in IF, CF for S critical field resistance. OCC is curve. Tangent of OCC curve is given the value of critical field resistance. RS is shunt field resistance. OCC of self-excited DC generator. No load curve for self-excited generator. The OCC or no load saturated curves for self-excited generators whether shunt or series connected or obtained in a similar way. The field winding of the generator whether shunt or series wound is disconnected from the machine and connected to an external source to direct current as shown in circuit figure. The field of exciting current IF is very rheostatically and its value read on the ammeter A. The machine is driven at constant speed by the prime mover and the generated EMF on no load is measured by the voltmeter connected across the armature. IF is increased by suitable steps starting from 0 and the corresponding values of E are measured. On plotting the relation between IF and E curve shown in graph figure. Due to residual magnetism in the poles, some EMF is generated even when IF is equal to 0. Hence, the curve states that little way up, the slight curvature at the lower end is due to magnetic inertia. It is seen that the first point of the curve is practically straight. This is due to the fact that at low flux densities, reluctance of ion path being negligible due to high permeability. Total reluctance is given by the air gap reluctance, which is constant. Hence, the flux and so generated EMF is directly proportional to the exciting current. Suppose that there is some residual magnetism inside the machine. From graph, resistance R is equal to V divided by I is equal to E divided by IF. In this particular case, the final steady state voltage depends upon the resistance of the field circuit or as a shunt field resistance line. It is clear that the shunt field circuit resistance is too large than when a small voltage is produced. There is a maximum permissible value for RSH such that the generator produces the sufficient voltage, rated voltage. This resistance is called critical field resistance. Shortly, say CF4. If the resistance line just lies along the slope, then with that value of field resistance, the machine will just excite. CF4, critical field resistance. The value of the resistance represented by the tangent to the curve is known as critical field resistance for a given speed. DC generator, electrical machinery 1. OCC of separately excited DC generator or voltage buildup of a shunt generator, that is field resistor and ammeter supply connections and field bindings connected and voltmeter are connected. Changing field rheostat is connected parallel to the generator armature. That is voltage built up of a shunt generator circuit shown in figure. Resultant graph shown in figure, that is voltage resultant graph shown in figure. Voltage built up of a shunt generator graph shown in figure, that is IFSSE. The curve obtained from voltage built up of a DC generator, that is gradually increased. Terminal voltage of a shunt generator graph figure C shown in figure. That is OF is whole of the generator EM, resultant generator EMF. Line OP represents shunt field resistance. OE represents maximum voltage machine will build up. Higher voltage built up resistance decreased. Critical resistance or critical field resistance line OR represents. RSS greater than RC generator will fail to excite. Generated EMF energy stored in the pole fields corresponding to field current OA line. Generated EMF is represent AC. AB is ohmic drop IF RSH. BC to overcome self-inductance EMF in the coil. Finally, we obtain OF as whole of the generated EMF. Voltage buildup of a shunt generator. Before loading a shunt generator, it is allowed to build up as voltage. Always presents same residual magnetism in the poles. Hence, a small EMF is produced initially. The EMF circulates a small current in the field circuit which increases the pole flux, provided field circuit is properly connected to armature. Otherwise, this current may wipe off the residual magnetism. When flux is increased, generated EMF is increased, which further increases the flux and so. Now the generated EMF in the armature has to supply the ohmic drop IF RSH in the winding, and to overcome the opposing self-induced EMF in the field coil, that is LDIF divided by dt, because field coils have appreciable self-inductance. EMF Eg is equal to IF RSH plus LDIF divided by dt. Hence, no energy is stored in the pole fields. Consequently, there is no further increase in pole flux, and the generated EMF with the give shunt field resistance represented by line OP. The maximum voltage to which the machines will build up is OE. If resistance is decreased, it will build up to somewhat higher voltage. O represents the resistance known as critical resistance RC, or called critical field resistance CFR or RC. If shunt field resistance is greater than value, the generator will fail to excite. RSH is greater than RC. If the generated EMF is in excess of the ohmic drop IF RSH, energy would continue being stored in the pole fields. For example, as shown in figure C, corresponding to field current OA, the generated EMF is AC. Out of this, AB goes to supply ohmic drop IF RSH, and BC goes to overcome self-induced EMF in the coil. Corresponding to IF is equal to OF. All of the generated EMF is used to overcome the ohmic drop. None is left to overcome. LDI by dt. That is LDIF divided by dt. That is ohmic drop. Conditions for build-up of a shunt generator. Build-up self-exciter. There must be some residual magnetism in the poles. For the given direction of rotation, the shunt field coil should be correctly connected to the armature. That is, they should be so connected that the induced current reinforces the EMF produces initially due to residual magnetism. If excited on open circuit, its shunt field resistance should be less than the critical resistance, which can be found from its OCC. If excited on open circuit, a shunt field resistance should be less than the critical resistance, which can be found from its OCC. If excited on load, then a shunt field resistance should be more than a certain minimum value of resistance R, which is given by internal characteristics.